the question how to study this shuffle algebra. I'm talking about the example, our example, but it is some technique which can be applied in general. So, well, what's the question? We have our shuffle algebra, and in our special case, this is algebra E, because the sum of AN, and AN, I just write in E. What is this? It is the space of polynomials, of rational functions in N variables. And here we have symmetric Laurent polynomial, and the condition is that polynomial is 0. I just write again. Or open. When you, if you look to this, that you have, without any connection with any shuffle algebra and so on, you have a problem about symmetric polynomials. So, what we have here? Let us forget for a moment about this, and let us look to the set of all symmetric Laurent polynomials in M variables which are 0 on such submatrix. So the set, the space of all such polynomials forms some ideal, evidently ideal in the symmetric polynomials in variables, and which determined by this condition, it means that there is 0 on a submanifold of codimension 2. No, if you are, we want to describe this ideal by some way. And in general, if you just have n-dimensional plane and some submanifold to dimension 2 special of such kind, it is not so easy. It is not full intersection like this, so it is just some ideal. But in this case, we can use some technique, and this technique, at least I call this technique by Gordon filtration. And I'll explain soon why I use this name. But Gordon filtration usually, this is the following thing, that if we take symmetric polynomials, suppose not Laurent polynomials, but just usual ones, x1 and so on, xn, symmetric, yes. Then, no, they are just functions on Cn over Sn, and no, anyway, we know that this quotient is isomorphic to Cn, but for our purpose, I want to use that on this quotient. It is discriminant ideal. So Cn itself, this is the set of tuples of points, and this discriminant ideal is no, C and this are the quotient if we are taking it quotient by a sensor, we do not take into account the order. But discriminant ideal discriminant is the set when at least two of them coincide. So discriminant is such that say x1 equals x2. And then discriminant is divided here. Yes, and this submanifold here, it is not. No, it appears very many times in different questions, and the standard way to study it to decompose it to components. And standard decomposition is the following. So the discriminant divisor D, it has stratas. Stratas in these divisors are labeled by Young diagrams. Namely, if we Young diagram, it is like this. Maybe like this, and to, for example, number of boxes have to be equal n, and to such diagram I can correspond the strata here, where say x1 here, x2 and x3 they are equal because they are here. Here we have x4, x5, x6, and we also suppose them be equal, and so on. Here x7, x8, and so on. So how to think about this? That we have line, and we are the axis coordinate of points, we can call them particles, and if we have Young diagram, it means that this is submanifold here, where this is it, but this is equal to this, they collide. These three collide in the group, and then four collide in the group, and then extra four collide in the group. Yes. And therefore, we have such collections of submanifolds, which labeled by Young diagram, and using this set of submanifold, we can consider, in principle, not by unique way, that filtration on in space of symmetric polynomials. And how it is usually doing that? No, I said by many ways, but to make up the filtration, let us do the following. We have a set of Young diagram, and on Young diagram we can consider so-called lexicographic order. no, lexicographic ordering, it means one Young diagram is like this. Second is like this. And this is bigger than this if this is bigger than this. If equal, then this bigger than this. So this is what is called lexicographic ordering. And, no, as I said, for our purposes, it's possible to use different ordering. For example, therefore, it means that on space of symmetric function, we have the filtration labeled by a Young diagram and the component, the ideal, which is labeled by Young diagram. It means that there are functions which are zero on strata corresponding to this Young diagram and strata which are, you know, in my ordering, which are bigger. So, it means what? That we, for example, maybe it will be clear. If n equals 2, maybe it is not interesting. First interesting case, n equals 3. So we consider in this case what? We have 3 Young diagram like this, then like this, and then like this. And then I order, according what I said, I order them by this way. Yes, and now let us talk about the stratas. And well, what is corresponding to this diagram? It is just set of x1, x2, x3, so no conditions. So it means that, and so submanifold which is corresponding to this diagram is a whole. Since here we have a case where x1 equals x2 and then x3. And we have x1 equal x2 equal x3. Yes, therefore we have such kind of stratas. And these stratas, from the point of the corresponding filtration on a polynomial in 3 variables, symmetric. One, it is mean what? The biggest is corresponding to this diagram. This is all things. Then we have first ideal, which are 0 if ordering is what? We have the bigger, the whole things. Then we have smaller things, which is equal 0 if x1 equal x2 equal x3. And we have smallest, which is equal 0 if x1 equal x2. Again, it is opposite with what I said. But filtration is like this. First,
the ideal corresponds to the biggest strata.
not strange, but I confused maybe 2 times. But, but anyway, the situation in the polynomials in 3 variables is just this. So it means what? It means that it is incorrect what is written here. Probably, yes. So let us try to say this in a better way. Anyway, so in this case, the biggest element in my filtration is a whole thing. Then it is no conditions. And next, it is 0 if x1 equal x2 equal x3. So this is biggest. Then this is corresponding to, in my notation, the diagram like this. Yes, then the next one is which, so here function which has 0 on this diagram, just on this diagram. Here function 0 when x1 equal x2. And this strata is corresponding to this one. Yes, and the last one is just 0, and it is corresponding to a strata like this. Anyway, so now it is better.
But you have 4 levels, but 3 diagrams.
What?
You have four levels.
But next,
This one
but
is
the last one is 0.
Yes, but what first one? All ring of polynomials.
All ring of polynomials corresponding from this notation to nothing. Or no, you see, this diagram gives me submanifold. Anyway, I cannot say it better. It is not this much. No, if you anyway, so by this way, we can, no, by a similar way, we can define filtration in any number of variables, and it is called by Gordon filtration because of the following. So you can write, for example, in this case, what? You have the whole space of function. Whole space of function is they are symmetric. And so we can write a character of this. It is 1 over 1 minus q, 1 minus q square, 1 minus q cubed. No, because it is Gilbert series of corresponding algebra. And then you can write that what? No, because we have a filtration, this character has to be equal the sum of a character of quotient. Now, first quotient is what? I have the full thing and factorize it up to function which has 0 on the whole diagonal. and the quotient is function in one variable, in coordinate of this. So we can write 1 minus q here. And next, what we have to do. No, it is also easy to write down the character of the lowest part of this, because this consists in polynomials, symmetric polynomials, which are 0 when 2x is coincide. Therefore, polynomials here have a form square times symmetric polynomial. Therefore, third term is what? Q6, 1 minus Q, 1 minus Q squared, 1 minus Q cubed. Then we have one more term. One more term, what we have to do? We have to take polynomials which are symmetric in x1, x2, x3, which are 0 on the diagonal, and we have to factorize them by the lowest thing. So what is our question here? I have functions in 3 variables, but I can consider which are 0 on this diagonal, but we are interested in substitution. Image C, y, x3. No, because I want to take this function and substitute x1 equal x2 and denote it by y. And so it means that from the point of view of stratification, I have two-dimensional strata, and I have coordinates of this strata. One is y. No, this strata is 2 points coincide, and 1 point is moving somewhere. Y is coordinate of this strata, x3 is coordinate of this strata. And then you see that after, if I have symmetric function and restricted by this way, x1 equal x2, that I get some function in 2 variables. But not arbitrary one, it is some condition. But this condition, maybe we discuss it a little bit later. But if I take symmetric function in 2 variables, such which is 0 when x1 equal x2 equal x3, and substitute x1 equal x2, then I get function in y and x3, which is evidently 0 if y equals x3 because of this condition. But actually, more than that, the order of 0 here equal 2. It is very easy to check, to see. And the fact is that after that, this will be subjection. So if I take some function here, which has a form y minus x3 squared times some q y x3, then this is the image of function with such properties. From this, we can say that term here is q squared, and here 1 minus q squared here. This is because this function is not symmetric in y and x3, because y double point and x3 is single point. And this is because there is 0 on the diagonal. And degree of this 0 is 2. And if you write such kind of, in principle it is some identity which can be checked without big problems. And if you consider 4 terms, then it gives you something similar. have more terms, how many Young diagram in 4 boxes you have, and Gordon, what is calling Gordon identity, it is follows from this formula. Gordon identity is not my subject, but it has some interesting identities anyway. And now, why I need it? I need it, no, even here we saw that the problem which we have here is similar to a problem there. So you have symmetric functions in 3 variables, and maybe because of some reason, you are interested in function which has 0, which is when x1 equals x2 equals x3. Then how to describe this idea? No, it's not very complicated, surely. But the way how it is doing on here, I consider on this ideal that 2-step filtration in 2 terms. And anyway, this ideal which is talking is what we have without this term. And on ideal I have filtration, 1 character of 1 term is this, the character of 2nd term is this. So it gives me some, not understanding, but at least something which helps to see what is going on. What we have here? Well, here I want to apply this Gordon filtration business in this case. But I will do it by the following way. Yes, I still use this discriminant ideal, but it will be more natural to shift the diagonal. And let me explain how it is going on here. So filtration is filtration on A1, which in this case just C inverse. No filtration, it is just as it is. And if I have A2, I want to understand this A2 by the following way. A2 is Laurent polynomials C1 over C2 yes, and I split or consider the filtration by the following way. So this is the whole A2, and it has subspace. So corresponding to the A2 is the whole space, and subspace is corresponding to this Young diagram, according to my notations. And this subspace, this is P are 0 if Z1 P is 0 if Z1 over Z2 equal Q C2. For this purpose, let us choose one Q. Therefore, in my space, I have subspace D Z1, Z2 divided to Z1 minus Z2 square. And here we have Z1 minus U2 Z2. Z1 minus U2 inverse. No, 2 terms, because if it is 0 here, it is zero surely in symmetry, Z1 and Z2. And subspace consists in these functions, and quotient is some function in one variable, and this is just value of this one on the this diagram when Z1 equals Z2. Now well, but from the point of view of the size of a space, it is clear what we are doing. Suppose if Q2 equal 1, then this part consists in polynomials without poles. And quotient, in a sense, they take care of a pole. And now let us look to the case of three variables. In three variables, what is this? We have functions in three variables. But the point is that we are interested in functions which are zero on the diagonal, and this the diagonal are here. Now, let us write this filtration, which I'm talking. This is really filtration, the lowest part of filtration. P are 0 if Z2 over Z1 equal Q2. This is the smallest part of filtration, and in this part we have similar kind of function, where P. Now in the top we have P, but maybe I use different letter, Z1, Z2, Z3, and here I have a product, Zi minus Q2, Z3 times product Zi minus Q2 inverse Bldg, and here the same Zi minus Bldg squared. Yes, and what will be the next term? Next term, what I have to do? I consider the such P, Z1, Z2, Z3, and restrict it to the diagonal. There I send P, Y, Z3, and such that Z1 equal Y, and Z2 equal Q2. Yes, and then let us see what kind of function we get. And now, because of this will condition, this function will be 0. If no, because it is 0 on Z Q2 in a diagonal Z Q2 Z and Q2 Q1 Z and the second diagonal. Therefore, this function has double zeros. 1, 0. No, you see that this is diagonal, and this is the thing. And because it is 0, if this, if they arrange by this way, then this function have as 0. No, in principle in 2 places. Then we can write it. If the 3 equal, it is what it is 3 equal, it is equal y times q inverse. And the second one, it is in understandable position. Yes, and I'm moving a little bit slower, but so let me skip a little bit in this place. But as a result, on the space A3, we have filtration labeled by Young's diagram like this. And like this. And again, logic is always the same. I have ideal in the space of symmetric polynomials. I have filtration on the discriminant ideals, and it gives me filtration on a space of function, and I just look what it is. And using this filtration, we can prove this theorem. Maybe better. How we say, but again, I did not explain it. So the result for A3 is the following. In the space, we have filtration smallest subspace is isomorphic to the space of symmetric polynomials in 3 variables. I explained that the smallest subspace is what? It is this times product xi minus zj squared And here we have the product the I minus Qj plus minus the I times Vj. So it gives me isomorphism between just symmetric polynomials and the smallest part of this illustration. Yes, and the next term of filtration is what? What we have to do? I have my functions from my space and from A3 and restrict them to the next component, and the result is the next term of the filtration is isomorphic. Just to the space of polynomials in two variables. Maybe Q, Y, X. Now what does it mean? It means that I have function from my ideal, I restrict it to the following strata, and I get as a result the polynomial in two variables times, like here, some factor which has degree 0. Number of terms in the top and number of terms in the bottom are the same. Yes, and the third term of filtration just are isomorphic to a space of function in one variable. Maybe to some other level, X or something like that. And such story will be true for any number of variables. And about the what follows from this Gordon filtration, let me formulate it by the following way. So, for me, it is easier to formulate the result of the size of the algebra by the following way. Well, so we have shuffled algebra, and A1 is C inverse, and in the last lecture I denote EI equal C power I. And now I need some kind of to study representation. There are two kinds of these representations, and what I need, let me first determine representation of the maybe first type, or I call it Magon representation. And this Mahagon representation is defined by the following way. Let fix U belong to C star and subspace in A1, which let us denote it A1 U, which is equal Z minus U times Z inverse. And now I take my shuffle algebra and generate it by left ideal. I want to factorize it by left ideal and generate by this. So I take left ideal is like this times A1 U. And a result of, because I factorize up by left ideal, it gives me right model no, because of some reason it's reasonable. I want to call this model the vacuum representation. Yes, and yes, and the question is, what is the structure of this representation? Anyway, this is a right representation of my shuffle algebra, and this representation is cyclic, and it generates by one, which we call vacuum vector. And after that, I can add to this vacuum vector by A1, but almost all elements from A1 acting by 0 because of this. So A1 is Z minus U times this. So it means that Zi minus U, Zi belong to A1. And it means that in terms of E, it means that if I act EI plus 1 minus U EI on the highest weight vector, it gives me 0. Therefore, let us call that we get something on the first level. We have only one vector there. Then I continue this procedure, and on this level is 0, this is level 1, and this is level 2. And it is more or less evident that I get how many vectors there, finite dimensional first of all, and it is possible to see that I get 3 vectors. And yes, and how to find it? First of all, no, let us look again. What is this? No, A1 that consists again. So I take part of this. For example, on degree 1. Here is in degree 1, A1, is function in Laurent function in the inverse, and subspace which I have to find consists in functions z minus u, and here we have c z inverse. And the quotient is one-dimensional, and this is what we have here. Now, what is happening on the next level? No, well, on the next level, in principle, we have function in two variables, z1, z2, and here z1 minus z2 square, and we have to factorize by this. And this is what? I take functions g1 times something from here. And these functions have a form z minus z2 minus u, say f z2. Yes, and then I have to look what is this? So what subspace of functions I have here? And anyway, this subspace of function will be subspace here, and this space is isomorphic to a space of symmetric polynomials in two variables, because it is this. And from the formula for a product, it is clear that this subspace, which we are talking about, is ideal here in the whole thing. And what is this ideal? The statement which is almost evident, or at least you can easily make up here calculation and see that the subspace of function of such kind, which is spanned by this, consists in function p of such sort, which are 0 when z1 and z2 are the following: z1 equal u, and z2 equal q1 u, q1 equal u, and z2 equal q2 u, and z1 equal u, and z2 equal q3. And these 3 points are support of corresponding ideal which we have here. And well, and because of the subspace is just function which has 0 in these 3 points, and therefore we see that the quotient is 3-dimensional. Yes, and if you want to make up this, no, in principle, we can go to the next step. So, well, we have one vector here, one vector here, and 3 vectors here. And how many here? If you want to determine it, in principle, you have to solve the same problem. Now, we have space of 3 variables, x1, x2, x3, but with real conditions, and factorize it up to ideal of similar kind. So you have to take here g, z1, z2, 2, and here is this 3, and here is this 3, and then span subspace by all such kind of function. It will be something here, and you have to factorize. Again, the problem to do it is just directly. It is not easy, and the best way to do it, to consider on this space the Gordon filtration, and here also the Gordon filtration. And in this case, you can not easy, but you can determine what quotient it will be. No, well, I will explain the answer, but unfortunately, we have not seminars which follow from these lectures, because for that it's much better to make up calculation not together, not me, but when all people do it. Yes, and it will be much better than what is going on now. But anyway, our question is following. We have A3. A3 is our description, that A3 is polynomial in 3 variables, symmetric one, but with real condition. So A3 is this condition, A3 is model over the ring of symmetric polynomials. A3 is a representation of algebra of polynomials in 3 variables. And if I want to determine what is here, I have to take quotient A3 up to something, and this something is sub-representation of ring of symmetric polynomials, also in 3 variables. Therefore, the quotient is the representation of ring of polynomials in 3 variables. And no, the remarkable property of this is that this quotient is finite dimensional representation if it has some support at some point as any representation. And this is some finite number of points. And the multiplicity of each point in this case is 1. So it means the following, that so first of all, before I describe the support, I will say the answer. Our representation as I said, is grading. Now we describe on the first 3 grading till this moment, and the dimension in to the number of plane partitions in n boxes. So that picture, which is good to have in mind, that the structure of the actually the basis of this representation is labeled by plane partition. For example, here we have just empty. Here we have one box. Plane partition is just boxes which you put to the corner of the room. So it is one box is here, and the support of representation was point U, and we can put U here. And for example, here, this part is corresponding to a plane partition in three boxes, in two boxes. And they are, so we have plane, we have box here, box here, and I can put next box here, here, and here in three positions. And then we have these three things. And if you have, and the formal rule is following. So you have a following picture. This is our angle, and three axes are attached to each x, q1, or q2, or q3 here. And then plane partition in two boxes is what? We have one box, as I said, here, and we can put one box here, one box here, and one box here. And if I have plane partition in two boxes, in plane partition I have either U and Q1U, I have U and Q2U, and I have U and Q3U. And by this way, it gives me the description of support of corresponding representation. And if I have, for example, the next, in the next, it's also, but in this case, what we have, I can put box, then box, then box, just up. And so it will be U, Q1U, and Q1 square U. Or I have U, Q2U, Q2 square U. Or U, Q3U, Q3 square U. But we have three more. Three more, it means I put box here, and one here, and one here. So it will be U, Q1U, and Q2U, and U, Q1U, and Q3U, and U, Q2U, and Q3U. Yeah, and by this way, I get the description of support. So in general, you have plane partition, and you, by this way, as usual, you draw in the boxes U power Q1, Q2, Q3, and it gives us the support. Well, maybe And for example, we cannot say many things about, our algebra generate by EI, where I belongs to Z, so it has grading, but we cannot calculate the character for the algebra using this grading because I running from minus infinity to plus infinity. But we can cook up from this algebra some object where we can calculate grading and also determine the Gilbert polynomials. For example, I can take this representation and Mark-Magone identity says us that the character of this representation, Gilbert polynomial of this representation is 1 minus q, 1 minus q squared square, 1 minus q cube, and so on. Yes, this is one thing. And no, so I claim that Gordon filtration, if you carefully look, it gives us this. But now I explain one more thing where Gordon filtration also is using. Well, I have now before I consider the representation of my algebra, and in this I described this representation by this way, and because each space of representation is such quotient, and I claim that this quotient symmetric polynomials are acting there, and the support of this representation is finite set of points, it means that in our representation we have a basis. We just labeled by this plane partition. And actually this is some version of fixed point basis or things like that, but anyway we have it. Now let us change a little bit the problem. And the problem is the following. I have in my definition of shuffled algebra, A1 is C inverse, A2 is something, and so on. Now I want to discuss the problem about the different subalgebras. In shuffled algebra. Now, about subalgebra, we can ask the question that, algebra shuffle generated by EI, and first question, I can take some segment of this E, say E0, E1, E2, and so on, En minus 1, and just consider the subalgebra generated by this amount of generators, and it will be some subalgebra, and the question is what is the character? In this case, it will be some algebra which bi-graded, because all my algebra is bi-graded, and this is also. But now in degree 1 we have n elements, in degree 2 we also have finite dimensional number of elements and so on. And we can ask about the character of corresponding algebra. And also we can ask similar question of such sort. And I want to answer to these questions more or less by the following way. And the next part of my story will be the I want to use some simple algebraic geometry, but very small amount of this geometry to describe, to give the explicit construction of this subalgebra and some similar subalgebra in a shaft. Okay, so how to describe it? First of all, what is this? They are space with the basis 1, z square, and z and minus 1, and they are just polynomials in one variables, but degree restriction we have, and it is n-dimensional, and this space we can identify with the following. We can take CP1, and we can take linear bundle here, which is O n minus 1. And this is usual the beginning of any algebraic geometry, that the space of sections of this bundle can be identified with this. Space of sections, let us denote as in algebraic geometry people usually do like this. Okay, what is going on when I consider star product of functions here? So I have such function which belongs to a section of this, and take a product to some other function from this space, and what I get? I take f, which belongs to H0, O, n minus 1, J, also from this space, and I calculate f, and how the shuffle product is working. So, no, we have symmetrization there, but we symmetrize what? We take f times g z2. What is this? This is the section of what? So we have CP1 times CP1, and we have O n minus 1. No, it is just such kind of tensor product of two bundles. One of them is here and one of them is here. And f times g is the element of this. Then we have here the function lambda. But what is the function lambda? Function lambda is z1 minus u1 is 2, z1 minus u2 is 2, z1 minus u3 is 2, z1 minus u2 u. So what is this? This is function, but this is function on CP1 times CP1, and it has pool of degree 3 here, and 0 of degree 3 here. So what is this? It is a rational function on CP1 times CP1, which can be described by its divisor, and divisor is, you see, from this. So, well, it means that if you calculate this, fc1 times fc2 times this one, what you get from the point of view of algebraic geometry? It means that you have this section of this, which is this part, and then you calculate the product to this, and it gives you what? Let us put hat here. The such result gives you a rational section of O n minus 1, which has pull on the diagonal of degree 3. And maybe, I don't know what's the best way, best notation, we can put minus 3 here. For example, it's not standard notation, but it is clear what I mean. Anyway, after that, you make up the symmetrization, and symmetrization, as I explained, cancel one pole. And so after that, we see that result of a star product is the element O n minus 1 first of all symmetric, and it has a pole of degree 2 here on the diagram. And by star product, we can get all functions of such sort. Then we can ask, what is the dimension of this space? Now, how to determine it? What is this? No, we can make this exercise even right now. Can somebody say what is the dimension? No, from our goal, it is clear. This space pretends to be the quadratic part of the algebra we generate by this. And I want not to use the algebraic relation and so on, but I want to identify the quadratic part with the section of this bundle. And in principle, well, now let us look. Suppose we have a poles here. It means that I have O n minus 1 and the symmetric part. No, the dimension of this space is clear. The dimension of this is n, so it's n and plus 1 over 2. But now, what I do? Now my space is a little bit bigger. It means that it's a section, but this section, they have pull on the diagonal of order 2. And so it means that this number becomes bigger. But how much? No, actually it will be n plus 1 times n plus 2 over 2. No, what's happening? No, I like the following thing. That, no, it is simple things, and maybe it is good to understand. Well, so O n minus 1 is what? This is n-dimensional. This is a section of O n, and this is n-dimensional space, and it can be identified with n-dimensional representation of a set 2. If you take just before any symmetrization, if you take like this, then what is this? It is bundled on CP1 times CP1, but the sections are tensor product of n-dimensional representation for SL2 times n-dimensional representation of SL2. Then n-dimensional times n-dimensional is what is this? It is, as representation, it is sum of 1 plus 3 plus 5 plus 2n minus 1 dimension representation of SL2. How to see this decomposition from the point of view of a tensor product? No, it is easy. You take this and restrict it on the diagonal. Restriction, dimension of restriction of the diagonal will be this. If you consider the section which has 0 on the diagonal and take them and look to and restrict on the diagonal also. So it means what you can do. You can take section which has 0 on the diagonal, but you can look on the diagonal the first term, derivation. So it gives you the next term here. Well, I only want to say that on this tensor product, you have filtration. The sections which are 0 on the diagonal, the sections which have double 0 on the diagonal, triple 0, and so on. And on the space of section of this tensor product, you have filtration. And you can ask about the dimension of each floor. Each floor surely will be a SL2 representation, and it will be reducible representation. And each floor here corresponding to this term, 1, 3, 5, and so on. And now, suppose, well, if you are talking about symmetric sections, then 1/2 of this decomposition survive. These next, and so on. So this survive, next not, next survive, and so on. But it is symmetric. But before symmetric, suppose I consider the sections of this bundle which have poles of order 1 on the diagonal. Then this space becomes bigger after that. How much? But if you look to this, it is easy. You can see that you add here to n plus 1. And if you consider zeros of bigger degree, you are going in that direction. If you admit poles, you are going to that direction. And so if you put here -2, then we add here 2n plus 3, and so on. And so this space becomes bigger, 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 and no, it is easy things. It is, for me, it's just some way to remember what is going on, but it is standard things. But here, what we have? We have, first of all, we had symmetric part of this, and it starts, what I said, with 2n minus 1, then 2n minus 5, and so on. Yes, this is symmetric, just symmetric, without any poles. As I explained, it is this. And then if I admit pole of order 2, it means it adds 2n plus 3. And I want to understand this additional term as the contribution of this pole of order 2 in this place. Yes. Anyway, I wrote this, and maybe it's correct, maybe not. It has to be correct. But it's some way of checking. Just subtract them and see that this or not. Well, anyway, this is the way how to do it, and now about the construction of the algebra, I mean, which generate by this part, how to do it. Well, so it is some kind of version of shuffled construction. In this case, it is what? We have CP1. We have bundle O n minus 1. And as function lambda, what we have? In function lambda, we have rational function on CP1 times CP1. No, with the properties, no, the property of this function that, well, we know it's divisors, so poles on the diagonals of degree 3 and zeros on 3 shifted diagonals also degree 3. Yes. After that, I make up my product, and this product gives me what? These products now in degree 1 I have O n minus 1. In degree 2 I have O n, no, what I have? I have CP1 times CP1, yes, and I have O n minus 1. And here minus 2, and just section of this. Anyway, it is always working by the same way. So if I go to grading, say, K, then I get something on CP1 times CP1 times CP1, and here what we have. First, we have linear bundle, which is O n minus 1. Even better to consider tensor product and write minus 1 in the top. So it means what? It means on this CP1, on this product, I have discriminant submanifold, and I have to, and here this is bundle, linear bundle, and I have to subtract discriminant divisor 2 times. No, from the point of view of formula, it means the section is something divided to the product, di minus dj squared. This is just a formulation of the things. Anyway, this object surely will be a linear bundle on this. And it is not a big deal to write down what bundle will be. Linear bundle on CP1 times CP1 times CP1, especially symmetric one, is a tensor product of some O. And you can find what it is without problem. Anyway, we are interested in the sections of these bundles. Yes, and it is just finite dimensional space. But now we need such section which satisfy Will condition. So it gives us, so anyway, it is some kind of problem now, just determine some finite dimensional space. I have vector bundle on CP1 and CP1, and I'm interested in symmetric sections of this bundle which satisfy in Will conditions. And actually, by this way, I have what I mean here, some sort of algebraic geometry description of subalgebra, which is generated by 1 z square and so on, z n minus 1. Well, and now, no, the story in principle is the same. That if you really want to determine the dimension of the space, it is hard to do direct. Again, you have to filter it by a Gordon way and determine the degree, now it is finite dimensional space, on each stage. And it gives you, in some sense, the description, and this description will not be very complicated in this case. But no, this is important, but I need a little bit more. And now I want to use this algebraic geometry construction for defining in a shuffle algebra the big commutative subalgebra. Actually, the story is the following, that as I explained yesterday, well, by many ways, it is possible to prove the following proposition of theory. First, the algebraic formulation. Well, I discussed yesterday the cubic relation, and I said E0 compute with E1 and E1. Today, if it will be possible, I want to discuss the algebraic geometry meaning of these things. But anyway, we have here, because if we believe that this is correct, we have this element and this element, and I claim they commute. But actually, we can do more than that. We can take E0 and E1 and E minus 1. This is the beginning, or at least two first elements of commutative algebra, subalgebra in this shuffle algebra, and the next element can be constructed by the following. Let us take E1 and take a bracket with E1 and E minus 1. And then take the bracket with E minus 1. It will be the next thing. And then it is possible to make it a little bit shorter. Let us denote it. No, or maybe it is not necessary. The next element will be the following. E1, E1, E minus 1, then E1, E minus 1 begin, and then E minus 1. And so on. So I claim that the whole sequence of elements which we construct by this way commute. But let me just say a little bit more precisely what is. Schematically, what we are doing. We have E0, we have E1, we have E minus 1. So this element is the bracket of this and this. It is here. Now, what is my next step? I take bracket this and this. It is this element. And then take bracket this and this. It will be U. Then what I do on the next step, I take, now I have three elements here, and I claim that they commute. And suppose I want to, and I have three more which I use for constructing this. Again, this is the bracket of this and this. Again, what I can do, I can take this element and take bracket with the same, this one, here. And after that, take bracket this and this. It will be this one. If I want to construct the next, I take this, bracket this and this, construct something here, and take bracket with this. By such kind of construction, I get a sequence of elements. And this is just starting 1, 2, 3, 4 of them, and I claim that all of them commute. And this is construction, and in a special case, this is one way of constructing the Macdonald operators, but in our case, it was just commuting subalgebra inside our shuffle. No, anyway, the constructing of commuting algebra, this is important things, and this special theorem you can prove either pure algebraic way without any relation with shuffle, but in this case you need, no, for example, we almost have the definition of our shuffle in terms of generators and relations. Yes, so, and using this description in principle, such proof of this theorem exists. But other way to see geometrically what it is. So, what is the problem? Our shuffle algebra consists in some polynomials here and some function here, and one way to say precisely what function p here we have to take to get the elements from this commutative algebra. So this is the question. And in this commutative algebra, it starts with A0, and so at least this is we know from the first place subspace here we take 1 from here, and it is just our E0. But how to describe these brackets and what is going on in degree 2, 3, and so on, this is the problem, and I want to present the answer. And this answer actually in a spirit of construction which is here. And now it is possible to say it without any algebraic geometry and things like that, but I like this language, and so I want to use it. But I can say that it is not necessary, it is easy to translate. Anyway, so before I took as starting point CP1 and some bundle on CP1, and then I produced some algebra, which is subalgebra in our shop. In principle, construction of such kind is working. It is not necessary to take CP1 as a starting point. In principle, it is possible to take we can take even any manifold, but it's too much. We can take as CP1 algebraic curve at least, and the construction, just construction of shuffle type algebra. In this case, how it is going? By the same way, in the simplest case, well, I can take, no, in our case, E will be the elliptic curve, even more, it will be degenerate. But in principle, we can do it in general. I can take the curve, I can take bundle, yes, and I can take even on E times E, I can take rational function lambda, which have pool somewhere, suppose on the diagonal of some degree, and it has somewhere it has zeros, yes, and we can make up the same construction. So I start with zero section side, and on the next step, if it is something like that, I get 80 side times side. Here it can be some pole, suppose 2, and symmetric function, and so on, and also will condition. Now, at least, no, I only want to say, maybe not, I do not want to go into details now, but by this way you can get some rather interesting algebras starting. No, it is not known much if E is genus bigger than 1, as usual. But if elliptic curve, we have a lot of information and many interesting examples of algebras. And maybe if you heard about Feigin scanning algebra with, and maybe initially with 4 generators, that this algebra can be constructed by this way. So this is a special. But for us, E will be not so complicated, even not a bit curve, but it will be what is calling the generator. It is just this, it means as manifold we have CP1, and here we have north pole, and we have south pole, and we identify them, and get as a result this one, and point is the following, that, well, I want to no, I explained some construction. Well, I O n minus 1, and then it has to be algebra, and it will be algebra which generates by 0, 1, 2, and so on, n minus 1. But this is the key in the case when n is bigger than 1. If n is 1, if we take only E0, it's wrong. And then the version of this construction, when n equal 1, gives us just commutative algebra, which I'm talking about, but how this construction for n equal 1 looking differently, and I want to describe what is this. To start with, I want to think as E is such kind of algebraic curve, just CP1, we identify two points, and E0, our E0 is what? Our E0 is just 1, so it is a section, the only non-trivial section of a linear bundle, trivial linear bundle on CP1, but surely it is 1, so it means that we can glue what I do here, north pole with south pole, and this E0 will be the section of bundle, maybe O here also. Yes, and then what else? There, before I said that function lambda is a rational function on CP1, and CP1 with 0 and poles with some prescribed place, but actually lambda is the function on not CP1 times CP1, but this times this. No, this is, excuse me, this is this. This is why. This is not completely evident, and this is because Q1, Q2, Q3 equal 1. And it means that for this function, it means that if I go to 0 to infinity, the limit will coincide. And because of this, no, actually, it is the statement that lambda, no, CP1 times CP1 has a map to this curve times this curve, and actually lambda is given here. No, I think it is clear, and it is clear that it is because Q1 times Q2 times Q3 is 1. Otherwise, it's wrong. And but suppose you believe me that it is so. Now I can use my anyway. If it is so, and if it is here, then. What kind of algebra we get? No, well, I start with maybe E, and let E be notation for this. And on this E, I have trivial bundle, O, and section of this O is one-dimensional space, and this is my E0. Yes, and now what is going on in degree 2? Well, construction is working always by the same way. I have E times E, I have O times O, and then my sections now, they are, I have to put -2 here, and the question is what's happening? No, before I described how it was, that before it was not this but CP1, here we have O, and if it was CP1, so we got what? We got 1 plus not 3 but 5, maybe 6. No, for CP1 times CP1, what was it? It was CP1 times CP1. It had trivial representation here, trivial representation here. But that on the diagonal, I have a pool of order -2, and consider the section. And if I have pool -1, I add 3, if -2, I get, yes, and the dimension is big. But now I'm working with the generate elliptic curve with this. And it means that if I take, just practically, if I take section of something, I want value in 0 and in infinity to be the same. This just means that 0 and infinity are glued together. And if you, well, but what we have to do, we have to find how many sections we have here, and we want to have symmetric sections on this of this bundle, and it is easy to see that, well, without -2, we have only 1 section, but because of a pool, we add only 1. The dimension of this space of this section will be equal, here it is 1, here it will be 2. And I claim that by this way I get some subalgebra here, and this, and so I go to E times E times E, and so on, and from the, if you want to forget about this, the generate elliptic curve and things like that, then the description from just explicit description will be the following. Now, in the shuffle algebra, we have subalgebra, and this subalgebra consists in function P and this function satisfies the following conditions. First, f is regular. On symmetric surely regular on CP1 times CP1, the poles are only here. Regular on CP1 times CP1 without a discriminant, and it means pole of degree 2 here. It's one condition. No, in our case, P of polynomial, but now we want this function as total things be regular on infinity and in 0. It gives us actually some degree restriction on P. But it is not all, and no, it's 0.2, but surely we have, I want to write down that real condition have to be true. It's not 2, it may be 0.0. Yes, but it is not all. The function is regular, but I can do the following. I can take f fix some z1, zl, and then take some parameter epsilon and put it in front of others. Zl plus 1, epsilon, zl plus 2, and so on, epsilon, zl, maybe z n. Yes, and no, because it is a regular such kind of function, here we want this to have limit when epsilon goes to 0 and epsilon goes to infinity. Because of this, such limit have to be finite, but the meaning of this condition that this limit have to be equal. Limit of epsilon goes to infinity and limit epsilon goes to 0 have to be equal. Maybe it is not completely evident immediately if you are not deal a lot with these things that such if you write precisely what was here, what if I play this the generate elliptic curve, and if I constant the algebra, that this construction has natural embedding into this shuffle things. And it is evident why, because in the generate elliptic curve we have open set with isomorphic to C star. Therefore, our algebra actually is subalgebra of something living on this C star, and this is just our thing. Therefore, this construction is just some algebraic geometry way to say what is going on 0 and on infinity. Yes, and this is just the precise answer, what it is. Well, and no, it's not a big deal to work with this, and people like Andrei Negut, they can easily work with such kind of definition. And, but from my, no, I mean to determine the size of the algebra and so on. But from the point of view of algebraic geometry, well, we have elliptic curve, yes? This is degenerate elliptic curve. And then we have bundle here, which is trivial. Well, and then what we are doing? So, no, this is trivial bundle, and the degree of trivial bundle is 0. Well, what is going on after that? I have E times E. then I take a pool for the 2 on the diagonal. I consider the sections of this. So here I have subspace of sections which are regular on the diagonal, and because they are symmetric functions, then it's only one such function. But if I take here sections, or section of functions, in this case, because it's just trivial bundle, which have pool on the diagonal and factorize, then it gives me section of some bundle on this degenerate elliptic curve. But this bundle will be square of this. And because it is trivial, this is also trivial. Then we, total dimension will be 1 plus 1. 1 is just regular, and this one, what is corresponding to this polar part. Total it will be 2. And what I said that because, no, about commutativity, it is not yet, but what I want to say that the E0 and the E0 square is surely elements from my algebra that all such conditions are whole. And it is not so evident that the element E1 E minus 1 actually belong to the same algebra. So, no, E1 and E minus 1, they are surely not. They are the E1 and no, because just on single, on elliptic curve, it is only one which satisfies our condition. And but if I calculate the bracket, because of our happiness, or I don't know what, this element belongs to this element. Now, what the next theorem says? It says the following. Well, let us consider this subalgebra of our shafts. Then first, what I want to say, that this subalgebra is commutative. This algebra as algebra is the algebra of polynomials in infinite number of variables. More precisely, we have what was written here. So I have one element E0 which has degree 1. It belongs to E1. One element, say E1, E minus 1. So it belongs to E1, second belongs to E2, one more belongs to A3, A4, and so on. And the whole algebra is just polynomial algebra in this query. Well, and so about how to prove it, but I do not want, but let me say a few words. Anyway, here you see that we have an which consists in a O function, and here we have subspace which consist in functions which take property. Yes, and first step, no, what is evident that this condition gives us stability. This is just simple checking. Just consider product and this. But about size, it is not so easy. Anyway, we can, as in many questions in this subject, can use this Gordon filtration. What I can do, I can take here our subspace, well, and this is the subspace